Okay, so that method is called, in general, called the line search. Line search. Okay, so the line search method works as the following. So if I have a general nonlinear function, so the contours are not going to be ellipsoids, but something pretty strange and not regular. So let's imagine I started with the S0 here, all right? And let's imagine I'm going to use a locally approximation that's actually a quadratic. So let's imagine the quadratic is something like that. Okay, so that's my, not very good at drawing ellipses, but imagine I have a I have a Taylor series, second order Taylor series expansion that has a contour like that. We know that this second order Taylor series expansion is going to have the same gradient and same testing as the nonlinear general function at this point. But elsewhere, we have no guarantees. Okay, so if we choose to optimize the second order Taylor series expansion, we get to this point, and then we can keep going. That is fine. Okay, this is the case that the method as it is works okay. But let's imagine I can have a different scenario. I can have a function like that. Okay, so I have a different function. And now if I start, for example, here, I have a local approximation. That's not a good point. Let me think of which point to use. Okay, let's actually use this point. Okay, so if we use this point, and let's imagine I have a local objective function. I have a local quadratic that looks like that. Not very good choice, I guess. So let's actually look at this point. So if I have a quadratic that looks like that, okay, this is going to be the optimal of the local second order Taylor series. What happens is that at the optimal of the local Taylor series expansion, my objective function is actually higher than where I started. That's not very good for convergence, right? So basically, in the previous case, I have J at S1. So let's say this is the we want to minimize the point. We want to minimize the point, and we want to basically have a series of S's that leads us to lower and lower and towards the minimum. So in this case, my J of S1 is less than J of S0, and everything is good. But in this case, my J of S1 is greater than J of S0, which can potentially, if happening repeatedly, it's going to lead to divergence. So that's the case we want to safeguard. The idea of line search is that if you look at the path that connects S0 to S1, the value of the objective function along that path actually would, even if the value of S1 is greater than the value at 0, the value would decrease first and then increase. So along this path, it's possible to find a point, for example, here, that actually has a value of the objective function less than that at S0. So the idea is at every step, instead of directly jumping to S1 without looking at the value of the objective function, we actually look at the value of S1 at S1 and compare that at S0. If the value has not decreased, then we want to perform a one-dimensional line search. Search the value of j at S0 plus a delta times S1 minus S0, right? So essentially this delta, as delta moves from 0 to 1, this parameter would vary from S0 when delta is equal to 0 to S1 when delta is equal to 1. So when delta chooses some intermediate value, for example, 0.5, it's more likely that I can find a point whose value is less than that of S1. All right. So basically, this line search procedure is going to guarantee that we are going to be getting a series of decreasing values of the objective function if we want to minimize it, or a series of increasing objective functions if we want to maximize it. So this combination of Newton's method and line search is one of the most robust way to maximize or minimize a nonlinear high-dimensional function.